Hello, good morning and good evening. This is your host, Mike Espina. Welcome back to Math Agility Live. This is our new platform where students can send in their math homework problems to our social media channels, and we will answer them via Facebook Live every Tuesday and Thursday from 6 p.m. to 8 p.m. That is Pacific Standard Time, Wednesday and Friday, 9 a.m. to 11 a.m. Manila Time. And tonight, we will be exploring and solving strength of materials problems. It is called actually, or it is also called mechanics of materials, which is an engineering subject that deals with the behavior of solid objects subject to stresses and strains. And also tonight, we have a special guest that will share some tips and techniques in solving strength of materials problems. So he's a graduate of BS Civil Engineering of St. Louis College in La Union, and he's a national quizzer for math and engineering. And also, he is a certified Vedic math teacher, and also he is also a tutor for math agility. Please, a warm welcome to Daniel James Molina. Hi,
Yeah.
Daniel.
Hello, sir. Hello, everyone. Yeah.
Okay, do you have any word to our audience today or to our followers?
So, to the followers of Math Agility, I hope you'll learn something from me today, and I'll try my best to give you the essential techniques and solutions and concepts needed for strength of materials.
Okay, okay. Let's go to the first problem. I'll share my screen first. Okay, can you see my screen?
Yes, sir.
Okay. So the first problem is about tension and compression. So here the pinned members shown in figure 1.10a carry the loads P and 2P. All bars have cross-section area A. So the question is determine the stresses in bars AB and AF. So I think you're gonna share your screen, Daniel. So let me unshare my screen first. All right, you can share your screen.
Okay. So, can you see my screen now, sir?
Yes.
Yes. Okay. So, the first problem deals with the tension and compression members. Um, and in this problem, we have trust members in a trust system. Okay. So, the problem asks for us to determine the stresses in bars A, B, and AF. So, from the given figures, we already have the free body diagram for joint A. And from the free body diagram, the forces on AB and AF are already exposed. So therefore, uh, we will use this free body diagram for us to solve for the forces first. Okay, internal forces that are acting on the two members. So as you can see here, we also have an exposed member, which is an exposed force, which is A sub x. That is the horizontal component reaction on joint A. Okay, so it's a roller support, so we only have one force here, which is horizontal, that is perpendicular to the surface shown in the figure. So for us to determine the forces on AB and AF, we must first solve for the reaction force at A. Okay, that is A sub x. So using the whole structure, okay, we we must take the sum of moments at C. And since we are in equilibrium, we must equate it to zero. So for our sign convention, we may choose to have counterclockwise rotation as positive. Okay, so since we are taking moments at C, the moments induced by the forces C sub x and C sub y, which are the reaction forces at the hinge, will be zero. So we are now left with 2p, p, and a sub x. So from there, we can solve for the reaction at A in terms of p. Okay, so we have a sub x. Of course, moment is equal to force times distance. So a sub x times times its perpendicular distance from C, which is this one. This is 3L. So a sub x times 3L. And then since it will cause a counterclockwise rotation about C, then it is positive. Then for the force 2P, it will cause a clockwise rotation about C. So it will be negative. So that's minus 2P, okay, 2P times its perpendicular distance from C, this one, that's L. And then for force P, it will also cause a clockwise rotation. So P times its perpendicular distance, that's 2L. And it will be equal to 0. Okay, so from there, we can solve for a sub x. That is actually 4/3 of P. Okay, so from there, we will substitute the value of a sub x, which is 4/3 of P. Since it's a positive value, then our assumed direction of a sub x is correct. It should be to the right. So using the free body diagram of joint A, okay, I will just redraw it here. So this will be 4/3 of P. And then we're going to have the force at bar AB. And then for bar AF, since we have here a force 4/3 P going to the right, then the force AF must have an inclination going to the left so that we will achieve equilibrium. All right. So we will change the direction of AF to this one. So the slope will remain one is 2:1 is the square root of 5. Okay. And then it will be going downwards to the left so that it will counter the force by AB and the 4/3 P, which is the reaction at A. Okay, so for us to easily solve for the forces at AB and AF, we can actually redraw the three forces for us to form a force polygon. So I'll draw first 4/3 P here, and then force AB here. Okay, and then I will relocate force AF so that it will close like this. So this is AF, and this is actually a right triangle with this inclination. Okay, so from there we can actually directly solve for AF and AB by using trigonometry. So since we have an angle here that is theta, this is actually the same with the angle formed by the slope of AF. Okay, so let's use tangent of theta that is actually 2:1 or 2. And it is also equal to opposite over adjacent, that's AB over 4/3 of P. So from there, we can solve the force on AB that is 8/3 of P, since the direction of the force is going out away from the joint A, then it must be in tension. Next, we can use cosine of theta. That is from the slope we have 1 over square root of 5, which is equal to adjacent over hypotenuse, that is 4/3 of P, all over the force AF. From there, we can solve for the force AF, that is 4 square root of 5 over 3 P. Since the direction of the force is going towards the joint, then it must be in compression. Okay? And then finally, since we are trying to solve for the stresses, then we will use the simple formula, that is the force over the cross-sectional area. Okay, so for the stress at AB, we have the force on bar AB, that is 8/3 of P, all over the area, the cross-sectional area of the bar, which is given as A. So therefore, the stress at bar AB is equal to 8P over 3A, and it should be in tension. And that is our answer for the stress at bar AB. Next, similarly for bar AF, that's also force over area. We have 4 square root of 5 over 3P all over the cross-sectional area, that is A. And this yields to the stress at AF, which is 4 square root of 5P all over 3A, and it should be in compression. And that is those are our two final answers. And that's the answer for the first problem.
Okay, thank you, Daniel James. If you have any questions or comments, you can write in on our comment section on Facebook, Instagram, and Twitter. Okay, so let's move to the next problem. Let me share my screen again, Daniel James. Should I call
Yes.
you Daniel or DJ?
Just call me DJ, sir.
DJ,
It's
okay.
shorter.
Okay, so for our next problem, this is actually about stress, right? So this is not emotional stress, but a physical stress. Okay, so the question is the bearing pad consists of 150 millimeters by 150 millimeters black of aluminum that supports a compressive load of 6 kilonewton. Determine the average normal and shear stress acting on the plane to section A dash A. Show the result on a differential volume element located on the plane. Okay. Okay. I will unshare my screen. Okay. You can share
Okay.
your screen, DJ.
So for the average normal stress and average shear stress on the given plane, the problem actually gave us a hint, which is to give the result to a differential volume. So let's have a differential volume here. A differential volume is a very small volume, very small portion of the given bearing pad. Okay, so let's have it at a side view. Okay, so we have here a 6 kilonewton compressive force, and then we must be having the plane AA. Let's try here. Yes. The important thing here is to show its inclination. So since we have a 30-degree angle here, so it's actually located here. But since we have an alternating interior angle based from the our differential volume, then the 30-degree will also be shown at this portion. So for us to solve the average normal and shearing stress at that plane, it will be easier if we will transmit that load and then expose that here. Transmit the load at the plane itself. Let's have this one, 30 degrees. And then actually we can have this length. Let's have this length as what the 150 millimeters. So for us to easier solve, okay. And then we can have the components of the 6 kilonewton force. But which component? Since we are dealing with normal and shear stress, we can define first the two stresses. So for the normal stress, from the word itself, normal, it must be perpendicular to the plane. Okay, the force must be perpendicular to the plane. And then similarly for shear stress, we have a force parallel to the plane. So we will resolve the 6 kilonewton force into its perpendicular and parallel components. So we have this one, and this one. Okay, so I will rewrite the portion here. So 30 degrees, and then we will have this one as the normal component, and this is the parallel component, or sometimes they call this as the tangential component. Okay, so for us to solve for the magnitudes of the two components, we will consider this triangle. So I'll place it here first. Okay, so we have this triangle. It's actually a right triangle, and then the 30-degree by angle chasing by geometry, it's actually located here. So the 6 kilonewton force is located in this part. The tangential component is here, and the normal component is located here. So for us to solve for the magnitudes, we will use trigonometry. Okay. So by trigonometry, the tangential component will be 6 sine of 30 degrees, since it's at the opposite side of the angle, and that is actually 3 kilonewtons, or 3,000 newtons by conversion of metric units. Then for the normal component, we will have 6 times the cosine of 30 degrees, and it's actually 3,000 square root of 3 newtons by geometry. It's basic geometry and trigonometry. Okay, then after solving for the forces, of course, we will go back to the simplest formula of stress, which is the force divided by the area. Okay, so we already have the force, then so we must solve first for the area. So for the area of the plane, we have this inclined length, and then we have the 150 millimeter width. So we have a width that is 150 millimeters. We can't see the width since it's perpendicular to our screens. And then for the length, since this is 150 millimeters, then we can have the cosine function that is 150 over cosine of 30 degrees. So therefore, our area is simply length times width, since it's a rectangular cross section. The the exact form is actually 15,000 square root of 3 square millimeters. Okay, we are trying to involve Newton and millimeter squared here, since it will be easier to show the unit for stress. Okay, I'll show this later. So first, let's solve for the normal stress. That is, of course, the force normal to the plane divided by the area. Okay, so the area perpendicular to the normal stress is actually the solved area a while ago. So we have 3,000 square root of 3 newtons divided by, okay, divided by 15,000 square root of 3 square millimeters. And Newton per square millimeter is actually megapascals. Okay, so this is actually megapascals. And then, of course, by using our calculators, or by simply solving for the simplifying for the value here, the normal stress is zero point 0.2 megapascals. 0.2 megapascals, or you can convert this into kilopascals. That is 200 kilopascals. But since it's stress on a given material, it's more often used. The megapascal unit is more often used in metric units. Then similarly for the shear stress, we will use the tangential component, or the parallel component, divided by the area parallel to it, which is also the same. That is 15,000 square root of 3 square millimeters here. And then the tangential component, that is 3,000 newtons. Okay, simplifying, the value is approximately 0.115 megapascals. And these are our two answers. So drawing the result, this is actually, it will actually look like this. So for the normal component, we have a zero point 0.2 megapascal stress, which is in compression. So the direction is towards the differential volume. And then for the shear stress, we have this one, 0.115 megapascal. So it out it's we have a wrong direction here. So it will look like this. And then actually if we will try to extend this to the state of plane, then there will be a counteracting shear force here that is the same magnitude. And then we have a normal force at the bottom, which also has the same magnitude as that of the normal stress. So it will look like that for if we will try to analyze it on the state of plane. So those are our answers for the second problem.
Right. Thank you, DJ. So let's move on to the third question. Again, let me share my screen to you guys. Okay, so for question number three, so the piece of plastic is originally rectangular. Determine the average normal strain that occurs along the diagonals AC and DB given the figure below. Okay, so let me go back again to, let's go back to DJ's screen.
Okay. Okay, so we are asked to determine the average normal strain on the two diagonals. So the formula for for strain is actually its deformation divided by its original length. So this will be our governing equation here. But for us to solve for the normal strains, we must first solve for the deformation of each diagonal and, of course, their original lengths. So it will be easier for us to solve first for their original length since noticing from the figure, we have a rectangle. So since we have a rectangle, then their diagonals must be of equal lengths. Okay, so the original lengths of AC and BD can be calculated using Pythagorean theorem, or actually we can have the knowledge of Pythagorean triples since we have a vertical length here that is 300 and horizontal length that is 400. So we have square root of 300 squared plus 400 squared, or by Pythagorean triple, that's actually 500 millimeters. So these are the original lengths of the two diagonals. Then it gets tougher since we will try to solve for the deformation of the two diagonals. So first, for us to solve for their deformation, it's actually what the length deformed minus the original length. So since we already have the original lengths, then we must solve first for their deformed lengths. So let's consider the deformed length of AC. So we'll use the first figure here. So for us to solve for the length AC, it's actually this one. We can project downwards its endpoints. Okay. If we project downwards the endpoints, we can see that this horizontal length here, let's say X, and then this vertical length here, let's say Y, will give us a the actually the vertical length should be here. Wait, somewhere here. Okay, somewhere there. This is the deformed joint A, and this is the deformed joint B, so that it will be easier to see. Okay, so for us to solve for the deformed length of AC, by Pythagorean theorem, it's actually the square root of x squared plus y squared, given from this figure. Let's say figure 1. Okay, so from figure 1. Okay, so let's solve for the distance x. So we have a 400 millimeter length AD. It will be stretched by 300 by 3 millimeters. So we have 400 millimeters plus 3 millimeters by looking at the figure at the x axis. But it shrinks by 2 millimeters due to the movement at joint C. So I'll show the 2 millimeters here. I'll project the 2 millimeter deformation here, and then the 3 millimeter deformation is somewhere here. Okay, so we have 400 millimeters plus 3 millimeters minus 1 millimeter. So the horizontal length is 401 millimeter. And then for the vertical length, that's why we have 300 millimeters stretched upwards by 2 millimeters due to joint C. This one. This is the 2 millimeter here. And then it will also shrink by 2 millimeters due to the vertical deformation of joint A. So the distance y will remain as 300 millimeter. So using the given equation, the deformed length of diagonal AC is actually, by using our calculators, is approximately 500.8 millimeters. So it's a little bit small in terms of its deformation. So the deformation of diagonal AC gives us, that's actually 500.8 minus 500, that's zero point 0.8 millimeters. So the normal strain of diagonal AC is equal to zero point 0.8 millimeters divided by 500 millimeters, or that is, it will be unitless. Of course, the units will cancel. So the average normal strain is equal to 0.0016. So that is the normal strain for the diagonal AC. Next, we have diagonal BD. So this is the deformed joint A and then the deformed joint B. So let's draw diagonal BD, that one. So let's have this as figure 2. So from figure 2, the length of the deformed length of BD is, let's have the horizontal length as x again, okay, and then the vertical length as y, okay. So we have the square root of x squared plus y squared. That's from Pythagorean theorem. So the horizontal length x, we have 400 millimeters, and then since B is stretched by 5 millimeters horizontally to the right, then we have 400 plus 5. So we have 405 millimeters. Joint D did not move, okay, based from the figure. So we only have a horizontal lengthening of 5 millimeters. Next, for the vertical distance Y, we have 300 millimeters. Okay, 300 millimeters. And then since joint B, point B is stretched vertically upward by 4 millimeters, we have plus 4. 304 millimeters. So from there, our deformed length BD is equal to, by using our calculators, we have approximately 506.4 millimeters. So therefore, our deformation of diagonal BD is 506.4 minus 500. So we have 6.4 millimeters. And then our strain is equal to 6.4 millimeters divided by 500 millimeters, which gives us a value of 0.0128 unit less. So these are the two average normal strains of the two diagonals.
So, all right. So let's move to the next question. Okay, let me share again my screen. Okay, if you have any questions or comments, please write it down on the comment section below of our Facebook account, Twitter account, and our Instagram account, Outmat Agility. So the fourth question is about combined stresses. So the question is, a bar of cross section 10 square centimeter is acted upon by actual compressive forces of 60 kilonewton applied to each end of the bar. Using Morse circle, find the normal and shearing stresses on a plane inclined at 30 degrees to the direction of loading. So let me just unshare my screen.
Okay. So the problem already asked um, for us to analyze the given problem using the Morse circle. So before we try to draw the Morse circle, we must draw a differential volume, and then we will label their normal and shearing stresses for us to easily solve for us to easily solve the given problem using Morse circle. Okay, so it's like a preparatory figure for Morse circle. So we have a differential element here, okay, and then we have normal stresses along the x and y, and then we have, of course, a shear stress that is about parallel to the given planes. So since at this portion we have a horizontal stress, so we have sigma y, sigma x, sorry, sigma x, and since it's a parallel to the x-axis, and then of course at the vertical part we have sigma y. Since it's since we have an actual compressive force, so we will also have an actual compressive stress. So it will be pointed towards the element. Okay. And of course, we have a shear stress here. So before we start drawing the Morse circle, we must solve first the values of these variables. Okay. So the problem shown has an actual compressive force of 6 kilonewtons applied to each end of a given bar. So it's like this. We have a bar here, okay? And we have a force here. Or it can also be like this. Vertical bar and then a vertical compressive force. Vertical compressive forces at each end. But from this figure, from the differential element, we will use like a vertical bar. Okay, so we have sigma y that is equal to what? Force over area. So the force is 60 kilonewtons. We will convert that to newtons, 60,000 newtons, divided by its area, that is 10 cm squared. We'll convert it into millimeters. Since in 1 centimeter, we have 10 millimeters. Okay, so this will be our conversion factor. But since it's in terms of an area of a given figure, so the we will square the conversion factor. So the stress at the vertical stress here is negative 60 megapascals. We will use a negative value since it's compressive. Okay, and then for sigma x, since there are no other given forces, we have 0 megapascals. And of course, the shear stress is also 0 since we don't have any shear stress at the given element. Okay, so from there we can now solve we can now draw the Mohr circle. But first we may have to write first the coordinates of the endpoints of a given diameter of the Mohr circle. So the endpoints of the Mohr circle can be sigma x for the x coordinate and then shear for the y coordinate. So sigma x, tau xy, sigma y, negative tau xy. It can also be flipped, okay? So we have 0, 0 for the first coordinate, for the first point, and then we have negative 60, 0 for the second point. So drawing our coordinate plane, oops, drawing our coordinate plane, it will look like this one. Sorry for that. Okay, I'll just sketch it here. So we have 0, 0, that's the origin here. Okay, and then negative 60, 0, the point is somewhere here. And then to draw the Mohr circle, bear with me, it will approximately look like this. Okay, okay. So for us to easily analyze the given problem, we can locate the center of the Mohr circle by using the midpoint formula. We have negative 30, 0. And then we can label the endpoints of the diameter. Here, 0, 0 is along the x plane. So this is the x plane. Okay. And then at negative 60, 0, this represents the y plane. Okay. Okay. So now the problem asks to determine the normal and shearing stress at a plane inclined 30 degrees to the direction of loading. So since the direction of loading is vertical, we will have to find a plane inclined 30 degrees from it. So it looks like this. Okay? So let's have a counterclockwise rotation of 30 degrees at the loading. Okay? So for us to convert that into the Morse circle, to draw that into the Morse circle, we will double the angle. So it's a property of the Morse circle. So from 30 degrees, we must have a plane here that is inclined 60 degrees from the y plane. So from here, we will draw 60 degrees there. So we have a plane. So we have this plane. Okay. So how will we be able to determine the normal and shear stress? We must find the coordinates of this point, sigma and tau. So this is the normal and this is the shearing stress. So it's actually using geometry. Okay, so we will project the point downwards so that we can find a right triangle. Okay, so we will have a right triangle here. So the normal stress will be this length here. So the normal stress is equal to what? We have the radius. Sorry. So we have R here. Okay, the radius. Plus, we also have a radius here, which is the hypotenuse of the given right triangle, but it will be multiplied by cosine of 60 degrees. So R plus R cosine of 60 degrees. And then for our shearing stress, we have this vertical distance here, which is actually R sine of 60 degrees based from the triangle here. So we can solve for the radius that is actually from 0, 0 to negative 30, 0, or that is 30 units. Okay. So from there, we can substitute that to the two equations. So the normal stress is equal to what? 30 plus 30 cosine 60 degrees. So the normal stress, actually it's negative, since it's at the left of the vertical axis. Okay, vertical coordinate axis, so it will be negative. N- this is negative 45 megapascals. So it is still in compression. Okay, and then next we have the shear stress, that is also negative, since it's below the horizontal coordinate axis at the Morse circle. Okay, so we have negative 30 sine of 60 degrees. So the shear stress is approximately equal to negative 25.98 megapascals. The negative sign here will only indicate the rotation that will be caused by the shear stress, but it's actually of the same um, sense. It's still a shear stress. Okay. For the normal stress, it's negative, so it's in compression. So these are our answers for the fourth problem.
Thank you, DJ. So let's move on to the fifth problem. Okay, let me just share my screen again. So the fifth problem is about uh, thin-walled pressure vessels. So if you can see my screen, so this is the problem. So the research deep submersible Aluminaut has a cylindrical pressure hull of outside diameter 2.6 meters and a wall thickness of 20 centimeters. It is constructed of 7079-T6 aluminum alloy having a yield point of 400 megapascal. Determine the hoop stress in the cylindrical portion of the pressure hull when the vehicle is at its operating depth of 5,000 meters below the surface of the sea. Use the mean diameter of the shell in calculations and consider seawater to weigh 10 kilonewton per cubic meter. So we have the answer here actually 300 megapascal, but the solution will be important in solving this problem. So let me go back to DJ again.
Okay. So in this problem, we will be dealing with thin-walled pressure vessels. So we have a cylindrical hull here. Okay. Let's draw a cylinder here. Okay. And then the cylinder is, of course, the top view will look like this one, since it's a hollow cylinder. It's a thin-walled one. Okay. So the outside diameter is 2.6 meters. Okay. And then the thickness of the wall is 20 centimeters, or that is actually zero point 0.2 meters. Okay. Then we are asked to calculate the hoop stress. Hoop stress is actually the circumferential stress. So if we will cut a plane at the vertical axis here, so the pinwalled pressured vessel will look like this one, approximately this. And then there will be an exposed force which will act at the walls of the steel, of the aluminum tank. Okay, aluminum hull. So it's the hoop stress will be this one. Okay. Okay, and then of course the pressure inside the tank will be this one, P. Okay, so from this can actually be derived, okay, by using summation of forces and stress over area, but we will have to approximate some of the parameters. And the derived stress here is actually P times D over 2T. That is for circumferential of the or the hoop stress. Okay, So the P here is the pressure inside the tank or the vessel. Okay, pressure. D is actually a diameter. Okay, diameter. Or actually, it's not just the any diameter. Okay, it's actually the inner diameter, since the stress will act somewhere here. The pressure will act somewhere at this portion of the tank, as you can see from the figure. Okay, so the pressure will act like this. Okay, I'll just sketch the forces. Okay, it will look like that. So we will use the inner diameter, and of course, T here is the thickness of the wall. Okay, so we should solve for the given variables first and then substitute it to the formula. So for the pressure, we sometimes it's already given, but sometimes it should be solved. So from the given problem, we have 5,000 meter deep below the surface of the sea, in which the unit weight of the sea is 10 kilonewton per cubic meter. So we can use from fluid mechanics, we have gamma, which is the specific weight of the fluid times the head h. So gamma is 10 kilonewton per cubic meter times 5,000 meters gives us 50,000 kilopascals. But since we will be dealing with stresses on materials, so we can convert this into megapascals. That is 50 megapascals. That's just by dividing kilopascals by 1,000. So we have 50 megapascals as our uh, pressure. Okay, and then our diameter, inner diameter, okay, is found by 2.6 meters minus what? We have point 2 here. Okay, so we have point 2 here and point 2 meters here. Okay, but the problem already gives us a hint here. We have used the mean diameter of the shell for the calculation. Okay, so for us to solve for the mean diameter, we are not actually solving for the inner diameter in this problem since it's given. But if it's not given, then we must use the inner diameter. So for the mean diameter, it is located somewhere in between at the middle. I mean at the middle of the wall, the given shell. So for us to solve for the mean diameter, we have 2.6 meters minus the thickness will be half of the thickness at the left side. Okay, it will be one half of point 2 here, and then it will be one half of 0.2 here. Or actually, it's a whole. Okay, one half from the left, one half from the right. So it will be a whole point 2. So 2.6 minus 0.2 is 2.4 meters. Okay, so from there we can solve for the hoop stress. So we have 50 megapascals times the mean diameter, we have 2.4 meters divided by 2 times the thickness of 0.2 meters. Okay? So the unit meter will be cancelled. So we will arrive with a stress unit, that's megapascals. So simplifying that using our calculators, we have 300 megapascals. So this is the hoop stress for the given problem.
All right, thank you, DJ. So let's move to the next problem, which is problem number 6. Okay, let me show you the. It's about actual load. Okay, let me just show you my screen. So number 6. So the A36 steel rod is subjected to the loading shown if the cross-sectional area of the rod is 50 square millimeters. Determine the displacement of C. Neglect the size of the couplings at B, C, and D. So given this figure, we will be solving the displacement of C. Okay, so I'll turn you over again to DJ to solve this problem.
Okay. So we are asked to solve for the displacement of C. Displacement of point C. From the figure, okay, we can conclude that whatever the deformation of bar CD, okay, the movement of C will not be affected. Okay. So we will not include in our calculations the deformation of bar CD. Okay. So for us to determine the displacement of C, we must have to solve for the displacement, deformation of bar BC, and then the deformation of bar AB. Since any movement of these two bars will affect the given point. Okay, we will add this algebraically. So whatever the direction of the internal forces, we must consider it. Okay, let's have lengthening. Okay, or yes, lengthening to be positive since it will go to the right. So it's let's have that as a positive, as its positive sign. Okay, so for the deformation of bar BC, we must use the formula for axial deformation, which is force times length over area times E, where E here is the modulus of elasticity, or it's sometimes called as the Young's modulus. P is the internal force, L is the length of the member, A is its cross sectional area. So we have PL over AE for bar BC and plus PL over AE of bar AB. Okay? We don't have any value for E, but since it's steel, then the value for E is 200 gigapascals. Okay? Or in megapascals, we have 200,000. Okay? Megapascals. That is for steel only. Okay? So we are left with the calculation for the forces, internal forces. So for us to solve for the force on BC, we can cut a plane. We can pass a plane cutting cutting bar BC, so that the internal force at BC will be exposed. Okay, so it will somehow look like this. So we have 2 kilonewtons here. This is point B, point C. Okay, and then we have a force of 4 kilonewtons here. Okay, so to counteract the two given forces, we must have a force of 6 kilonewtons to the left, which is actually the force on BC. That is 6 kilonewtons. Since it's going away from the members, so that's tension. Okay, so it will lengthen the given bar. So it's positive. Next, we solve for the force at AB. We will pass a section here. So it will look like this. So we have a 2 kilonewton force at the rightmost part. We have the 4 kilonewton force here, and then we have a 9 kilonewton force here. So we will expose the force on AB. So to counteract the given forces, so we have 4 kilonewtons plus 2 kilonewtons. Since it's going to the right, so we have 6 less 9 kilonewtons. It's going to the left, so we have 3 kilonewtons to the left. So we must counteract it with a 3 kilonewton force going to the right. So therefore, our force on bar AB is equal to 3 kilonewtons. Since it's going towards the member, so we have compression, it will shorten the bar, so it's negative. So substituting it to our working equation here, so the displacement of C is equal to, okay, force at BC, that is, force at BC is 6,000 newtons, okay, times its length, that is 1,500 millimeters, that is from 1.5 meters, divided by the area, that is 50 square millimeters, times the modulus of elasticity, that is 200,000 megapascals. Okay? And then we have plus, so the deformation of member AB, we have the force on AB, that's negative 3,000 newtons, times the length of AB, that's 1,000 millimeters, divided by the area, 50 square millimeters, times the modulus of elasticity, that's 200,000 megapascals. So simplifying, the the value is positive zero point 0.6 millimeters. That is actually our answer. And since the sign is positive, therefore the deformation, the displacement of C is going to the right. So zero point 0.6 millimeters going to the right. That is our resulting displacement of point C.
All right. Thank you, DJ. So let's again go back to my screen. And we are now in problem number 7. And problem number 7 is about shear force and bending moment. So given this diagram below, we need to draw the shear and moment diagram of the given beam. So again, let's go back to DJ's virtual board.
Okay, so we have here a beam. Okay, we are required to draw its shear and moment diagram. Okay, so we have here a concentrated moment, that is 3 kilonewton meter, and we already have the reaction at the supports, which are 1 kilonewton at C and at A. Okay, so we need not to solve for their reaction since it's already given. Okay, so let's have let's try to project the important points here. So point A, project downwards, B and C. There. So let's first draw the shear diagram. So it's denoted by V for shear. Okay. So let's have the zero coordinate here. Okay. All right. So let's try to solve for the shear force at A first. Okay, shear force to the right of A, not exactly at point A. Since we have a 1 kilonewton downward force, then the shear force at A is already negative 1. Okay, so since the the sign is negative, so let's go downwards by negative 1. We have negative 1 here. Okay. So since it's a concentrated load, so we directly go downwards. Okay, we follow the direction of the given load from the load diagram to the shear diagram. So we have negative 1. Next, since we don't have any loads along the beam AC, therefore there will be no changes along the way. Okay, since this 3 kilonewton meter moment here is a bending, causes bending moment, so we don't have any shear force at that point. Okay, so let's go directly at shear at C. This is actually shear at A. Okay, plus, so since we have a 1 kilonewton load at point C, so we have plus 1 since it's going upwards. So that is equal to negative 1 plus 1. So we have 0 kilonewtons. Okay? So it will look like this. Since we don't have any changes for the shear force along beam AB, so it will be constant at 1 kilonewton here. Okay, and then since we have a 1 kilonewton upward force, so we'll just go directly upwards so that it will end up at 0. Okay, right. So this is actually our um, shear force. So let's indicate this as a negative shear. So that's actually our shear diagram already. Okay, so let's project more downwards so that we can solve for the we can draw the moment diagram. Let's have the horizontal force here. Okay. Okay. So for the moment diagram, let's consider the moment at the important points. So let's have moment at A. Okay, since we don't have any applied moment at point A, or even we don't even have fixed supports, it's a hinge. So the moment at A should be 0. So our starting point is 0. Okay. Okay. So let's have the moment at B to its left. Okay. So the moment at B to its left is actually the moment at A plus the area of the shear diagram from A to B. So that is actually 0 plus what will be the area of the shear diagram? This is what? This is 2 meters, this is 1 meter, okay? So we have the 2 meter length times the height will be the shear force. So that's negative 1. Okay, so the moment at the left of B is negative 2. Okay, so the moment will be negative 2. So it's somewhere here, negative 2. Okay, so to connect the forces, the 2 points at the moment diagram, we must consider the shape of the shear diagram. So from the shear diagram at along AB, the shape of the shear diagram here is horizontal. So this is actually a 0 degree curve since it's horizontal. So for us to determine the shape of the moment diagram along that point, we must increase the degree of the curve by 1. So we have a 1 degree curve here, and a 1 degree curve is actually an inclined line. Okay, so let's just simply connect the 2 points here. So this is a 1 degree curve or a straight line. Okay, so we have negative 2. Next, we have um the moment at B to the right of B. Okay, we have the moment at to the left of B plus the concentrated load, the concentrated moment, which is 3 kilonewtons. We will add 3 since the direction of the 3 kilonewton moment at the beam is clockwise. Okay, so negative 2 plus 3, that's actually 1. Okay, so it's positive 1, so the positive 1 will be located here. Since it's a concentrated moment, so we will have an abrupt change in the bending moment. So let's just connect a vertical line here. That's positive 1. And then finally, for the moment at C, it's a roller support, so it's actually 0. But how will we be able to prove that it's 0? So we have the moment to the right of B, okay, and then plus the area of the shear diagram along BC. Okay, that's actually equal to 1 plus what will be the area of the rectangle here, that is 1 meter times the shear force, that's negative 1. So that is actually 0. So we have a 0 ordinate here. Since it is also a horizontal line at the shear diagram, so it should be an inclined line at the moment diagram. Let's connect 1 and 0 here. So there, we have already closed the moment diagram. So this is actually the moment diagram. So the areas above the horizontal gray line here is positive, and then We have here the negative signs. Okay. So we have a negative moment along AB and then a positive moment along BC. So these are actually our shear and moment diagram for the given beam.
All right. Thank you, DJ. So we're moving to the next problem, which is again similar to this one, which again, it's a shear force and bending moment. So if you have any questions and or comments about this problem that we're solving, you can write it at the comment section of our Facebook account, Twitter, and our Instagram. And also, you can tell us or shout out where place are you watching right now, so we would know uh, which part of the world are you watching this session today. So okay, so for problem number 8, again, so we need to draw the shear and moment diagram with the given beam below. So let me again turn you over to DJ.
Okay, so we will have a similar solution here, but it's a more complicated one since we have a distributed load at the given beam and we don't have any reactions. So, well, to draw for the shear and moment diagram, we must first solve the support reactions. Here at point O, we have a hinge support, but since a hinge support has two components, we have a vertical and horizontal component. But since the horizontal component of the reaction here is zero, at the same time, it does not affect our shear and moment diagram, so we will not deal with it anymore. So we just have to deal with the vertical forces. Okay, so let's label the points at the beam. Let's have the hinge at A, BA. We have the junction between the two distributed loads. Let's say it's point B, and then the rightmost portion, let's have it at point C. Okay, so let's solve first for the reaction at C. So to solve for the reaction at C, let's take summation of moments as at A. It should be equal to zero since it's in equilibrium. And then counterclockwise moment, let's have counterclockwise moment as positive. Okay, so the reaction at C will have a positive moment. That's times 8 as its lever arm. Okay, and then minus the resultant of the moment induced by the two distributed loads. So let's have the magnitude of the total load for the 100 newton per meter distributed load. Let's simply take the area. So we have 100 times 4. That's actually the area of the rectangle shown from the load diagram. And this is actually the resultant force for the 100 newton per meter load. 100 times 4 times its location times the location of its resultant. So if the resultant is located here, it's actually halfway through the 4-meter length. So that's 2 meters, right? Since it's a rectangle, so the centroid will be located at the middle. So times 2. And then same with the 200 newton per meter load, a distributed load. So we have 200 times 4 as its resultant. And then we have here the resultant force. So the location of the resultant force will be located at 4 plus what? Half of 4, that's 2 meters. So that's 6. So the lever arm will be 6 times 6. That's equal to 0. So the reaction at C, okay, so the reaction at C is actually 700 newtons. So let's write here 700 newtons. Okay? And then we can actually solve for the reaction at A, vertical reaction at A by taking moment at C. It can also be done by taking summation of forces vertical along the whole beam. Okay, let's have upward forces as positive. So we have the reaction at A plus the total load at the beam, we have 100 times 4 plus 200 times 4. And I mean, it's actually, sorry, it's actually minus since it's going down. The two loads are going downwards. Okay. So A minus 100 times 4 minus 200 times 4. And then we have the reaction at C that's upwards. So plus 700 is equal to 0. So our reaction at A is equal to 500 newtons. So 500 newtons. So from there we can now we can now draw the shear diagram. So let's project the important points. Okay. And then the horizontal line. Okay. So now for the shear at A. Okay, let's have the shear at A. So we have a 500 Newton upward force. So the shear at A is 500 Newtons. Positive. So let's have this one. Oops. Okay, let's have here 500. Next, let's solve for the shear at B. So to solve for the shear at B, we have VA, that's the shear at A, and then we have a downward distributed load here. So we have minus the magnitude of the total load along AB. Since it's a rectangle, so let's subtract it with its area, minus 100 times 4. Okay, so that's positive 100. So since it's positive 100, it's somewhere here, 100. Okay. Now we have a 0 degree load. Okay, we have a 0 degree load at the beam. So it we to solve to show the sorry, to show the degree of the curve for the shear, we add 1 to its degree. So it's a first degree curve along AB. So we have an inclined line here, straight line. Okay, we have a straight line from A to B. Okay, the given drawing is not to scale. Okay, so after that we solve for the shear at C. Let's have the shear at C to the left. Okay, shear at C to the left first. Okay, so to solve for the shear to the left of C, we have the shear at B. Okay, then minus 200 times 4. That is the that is the load at BC. So 100 minus 800, we have negative 700. So the shear will be negative at this point. Negative 700. Similarly, the shape will be a straight line. Okay. And then of course, the shear at C is equal to 0 already. Since from negative 700, we go upwards by 700 due to the 700 Newton reaction there. So we have 0 here. Okay, so from there, we have closed the shear diagram. So therefore, our computation for moment is correct. Okay, and we have already drawn the shear diagram. But before we proceed to the moment diagram, we must consider the part where the sign of shear changes. So this is at shear is equal to 0. We must solve for this distance. Okay, since we have two similar triangles at BC, we can use ratio and proportion. But for convenience, we can use a shortcut. Okay, so the length x actually here is the shear that is 100. We will divide it by the magnitude of the distributed load at BC. So 100 divided by 200, that is equal to 0.5 meters. So this is 0.5 meters. Okay. And then at the remaining portion, this is 3.5 meters. That's 4 minus 0.5. Or you can verify it by dividing 700 by 200. That's also 3.5 meters. Why should we solve for that distance? Since because along AB this is positive shear, and then for the first few portions of BC it's also positive shear. So we will add the two later, okay? And then of course we have a negative shear at the remaining portion of the beam. Okay? We will consider that in drawing the moment diagram. So let us project the important points. Project here and then project here. Okay. So we have the horizontal line here. So for the moment at A, since it's a hinge, so the moment at A is 0. Moment at A is 0. Okay. Next, we have the moment at B. Okay, wait. Before we proceed, let's name this point, the point of zero shear. Let's name it as point B. Okay. Okay. So the moment at B is equal to the moment at A. All right. Since it's a positive, we have along AB the shear is positive, so we add the area of the shear diagram for us to determine the ordinates of the moment diagram. So moment at A plus the area of the shear diagram along AB. So that is one half. It's a trapezoid, okay? So we have one half, 4 meters times 500 plus 100. So this is the area of the trapezoid. So the moment at A, the moment at B is equal to 1,200 Newton meter. So it's positive. So let's locate it here, 1,200. Okay. So now how will we be able to connect the 2 points? Let us consider the shape of the shear diagram. So we have a uniformly we have a straight line here that's a 1 degree curve. So the shape of the diagram here should be a second degree curve. Second degree curve, but how will we be able to draw it? We have two possible configurations. We have a concave upward parabola or a concave downward parabola. But notice that the shear from A to B is decreasing. So since the shear from A to B is decreasing, then the slope of the moment, the slope of the curve from A to B at the moment diagrams should also be decreasing. So since the slope is decreasing, we have from a vertical line, approximately vertical line going to a horizontal line since the slope will be decreasing. So let's draw a curve tangent to the two lines. Okay, there. So it will be concave downward. So I'll just show some of the tangent lines here. If you can see the tangent lines, the slope of the tangent lines will be decreasing. Okay, um, from there. So from a vertical line going to a horizontal line. So the slopes will be decreasing. Okay, so it will be concave downward. Let's label this as a 2 degree curve. Okay. Next, we have the moment at D. A moment at D, that is where the zero shear occurs. That's moment at B, okay, plus the area of the small triangle. So we have one half 100 by zero point 0.5. Okay. So the moment at D is equal to 1,225 Newton meter. Okay. So project it here. The moment is approximately here. Okay, so similarly, the slopes here, the shear from B to D, okay, from B to D is from 100 to 0, so that's decreasing. So the slope at the moment diagram should also be decreasing. So from vertical to horizontal, approximately, so it will look like this. Okay, okay. So we have 1, 2, 2, 5 here. It's also a 2 degree curve. All right. And then finally, for the moment at C, since it's a roller support, or you can also verify that by MD, that's moment at D, minus the area, minus the area of the shear diagram at the remaining portion, that's 1/2, 700 by 3.5, and that is actually 0. Okay? And of course, since the support at C is a roller, so the moment is also 0. So we have 0 here. And then from 0 shear to a larger one, to a 700 shear, okay, the slope will be increasing. Okay, let's disregard the negative sign. Just that the shear is from 0 to 700, so that's increasing slope, but it's going downward. Okay, so it will somehow look like this. So it's also a 2-degree curve. All right, so that's actually the moment diagram. So we are done with the problem. Yes, we are actually done with the problem. We have already drawn the shear and moment diagram of the given beam.
Okay, all right. So we're down to the last two problems. Okay, let me share to you again my screen. So, problem number 9 is about beam deflection. So, here again, the figure is given, and we need to determine the maximum deflection of the beam with a specified method, which is using double integration method. Okay, so let's go back to DJ's whiteboard.
Okay, so we are asked to determine the maximum deflection of the beam using double integration method. So for the double integration method, we have a governing equation here. So we have EI y double prime is equal to the moment equation. Okay, so I'll try to explain some of the variables involved here. Okay, E, this is the modulus of elasticity. Okay, I is the centroidal moment of inertia of the beam at the direction of bending. Y is actually the y coordinate of the deflected beam. So actually, the value of y will give us the deflection of the given beam. So we'll just have to maximize the value of y for us to determine the maximum deflection of the beam. Okay. So and then m of x, that's actually the moment equation of the beam at the last section of the beam. Okay. So first we have to determine the location of the cutting plane. Okay, let's have the leftmost portion as our origin. Okay, this is O, our origin, and then our cutting plane is actually here. Okay, at the last portion of the beam, so that it will cover almost all of our loads. Okay, and then we denote this distance as x, since the value of x will run from the left to the right portion of the beam. Okay, so we have EI, second, so we have EI y double prime. Before I forgot, the value of EI here also have a name. Okay, EI is actually the flexural rigidity of the beam. Okay, so it will define the strength of the beam in bending. Okay, so that's basically it. So for the moment equation, okay, we must take the value of the internal moment at the cutting plane. So it will be in terms of x. So before that, we have already solved for the reactions a while ago, since this beam is the same as the previous beam. Okay, so we need to expose the reaction here at the left support, since we will use this one, 500 newtons. We'll just have 500. Okay. For a second, we have 500. Okay, so taking moment at the at the cutting at the cutted section of the beam. Okay, let's have clockwise moments positive. Okay, so we have the 500 Newton force will give us a moment of 500 times x. Okay, 500 as the force, x as the lever arm. Next one, we have the distributed force. But this 100 Newton per meter distributed force stops at the midspan. Okay, it will not be applicable to the double integration method if we will stop at that point. It must be extended until the cutting plane. Okay, there. So there we have a 100 Newton per meter load from left to right, and then the remaining 100 Newton per meter. Okay, since we subtracted 100 Newton per meter at the 200 Newton per meter load. Okay, there will be a remaining distributed load here, but since it touches the cutting plane, so we have no problem with that. Okay, so we have two distributed loads now. Okay, it somehow look like this. We have a distributed load here, and then another distributed load here. So we have 100 here and another 100 here. So that 100 plus 100 is 200 at the right portion of the beam. So taking the moment due to the larger 100 Newton per meter load, we have 100 times x, that is the area of the rectangle, times its lever arm, that is the location of the centroid, that is actually x over 2. All right. So we also have the smaller 100 Newton per meter distributed load. We have 100 times x minus 4 times x minus 4 over 2. All right, so I will use a given grouping symbol, which is this one, bracket, for it's actually a singularity function. So I will use this one so that um, it actually means, let's have this one, a. Let's have the singularity function for a. This is equal to, it's actually a piecewise equation. This is equal to um, a if a is greater than or equal to 0, or that is actually if a is non-negative, we have the value for a. And then we have 0 if a is less than 0 or negative. So regardless of the value, once that the value inside the grouping symbol becomes negative, then it will be disregarded. Okay? Since the points which are less than 0 when the value is x minus 4 occurs here at the first 4 meters of the beam, it looks like the 100 smaller 100 Newton per meter load is not located at that portion, right? So we must disregard that moment. That is why we have used the singularity function. Okay. So we have 500x, simplifying, okay? So we have ei y double prime 500 of x minus 50x squared minus 50 quantity x minus 4 squared. Okay, we will not expand the x minus 4 squared here, since we are having a we have a grouping symbol that is a bit complicated if it is being uh, expanded. Okay, so now we have a differential equation that is in second order. So for us to solve for y, we will integrate it twice, right? We have y double prime, then integrating it twice, we have y. So that's why we call it the double integration method. Okay, so now we have e I y prime, since we are integrating it first. Okay, so we have 250x squared by integration. By power rule, we have 50 over 3x cubed minus 50 over 3 x minus 4 cubed. And then we will add the arbitrary constant, C1, since we are integrating it. And then, of course, integrating it for the second time, we have 250 over 3x cubed all over 25 minus, sorry, minus 25 over 6x to the fourth minus 25 over 6 x minus 4 to the fourth power plus c1x, and then of course a second arbitrary constant. Okay? So we need to solve for the arbitrary constant since we are dealing with a given beam. Okay? So to solve for the arbitrary constants, we need initial conditions. So basing from the figure, from the loads, okay, at x is equal to 0, that is at the left support, the deflection must be 0 since it's a hinge. From there, we can solve for C2 that is equal to 0. Okay, you can do that on your own. It's actually algebra. Okay, next, at the rightmost support, that is at x is equal to 8, okay, that's x is equal to 8, the deflection or y is also 0 since it's a roller. Okay, so we have C1, we can solve for C1 there, that is actually negative 9,200 over 3. So our deflection equation is EIY is equal to 250 over 3 x cubed minus 25 over 6 x to the fourth minus 25 over 6 x minus 4 to the fourth minus 9,200 over 3x. Okay, using differential calculus, we can solve for EIY prime and then equate it to 0. Okay, I'll just leave this computation to you. The value for x will be approximately 4.1106 meters. Okay, so this will be the location of the maximum deflection. Now, let's compare this to 4. Of course, this is obviously greater than 4. Therefore, our assumption that this term here is included. Once that this value is less than 4, then we may have to recompute this excluding the term highlighted. Okay, so since it's greater than 4, then our assumption is correct and our value of x is also correct. And then substituting it to our deflection equation, EIY is actually equal to negative 8,007.386. That's approximate. Okay, so therefore our y or our maximum deflection is equal to 8,007.386 all over EI. Okay, but since we have a negative sign, it will only give us the direction or the location of the elastic portion, elastic curve that is actually below the original elastic curve. So this is actually our maximum deflection using the double integration method.
All right, thanks DJ. So we are down to our last problem, and again we it is about shear force and bending moment. Let me share my screen to you again. Okay, if you have any questions or comments, please write down at our comment section below of our Facebook, Twitter, and Instagram account. So again, we need to determine in problem number 10 the maximum moment using this method, which is called the conjugate beam method. Okay, so let's go back to
Okay.
DJ's whiteboard again.
Okay. Actually, I have we have a typographical error here. It's not actually maximum moment. It's actually sorry. It's actually the maximum deflection. Okay.
Again,
Sorry
okay,
for that. Yes.
okay. So
Sorry,
maximum
sorry, sir.
deflection. All right.
Yes, it's actually maximum deflection using the conjugate beam method. So since conjugate beam method is actually another method in determining the deflection of a beam actually at any point. But since in this problem we are trying to solve for its maximum deflection. Okay? So since we have the same beam again, so we must arrive at the same value. Okay? We must arrive at the same value but of different methods. So let's try to draw the two reactions. Let's indicate the two reactions here, 700. Newton here. Okay. So for us to use the conjugate beam method, we must first determine the our conjugate beam, of course. A conjugate beam is a fictitious beam. Okay, let's compare that to the real beam. So we have real beam here. Okay, I'll just give some few concepts of the conjugate beam. Okay, so for the real beam, um, its slope, okay, the slope of the real beam is actually the shear of the conjugate beam. And then the deflection, okay, the deflection of the given beam, the real beam, is actually the moment at the conjugate beam. So it will actually be easier for us to determine the maximum deflection for the given beam, because we'll just have to take the maximum moment of the conjugate beam. But we don't need to draw the moment diagram of the conjugate beam. Okay, we just have to solve for the moment at that given point. Okay, so let's draw first the moment diagram of this of the real beam. But since based from our problem a while ago, the drawing of our moment diagram is actually actually complicated. So what we will need to do is to draw the moment diagram, but it should be by parts. Okay, let's have the moment diagram by parts. Moment diagram by parts. This is actually drawing the moment diagram for each given loading. Okay, so let's have the moment taken at point, let's say this is point A for the leftmost part at A. So our pivot point will be at point A. So the moment, wait, we have to extend, of course, the 100 Newton per meter again, so that it will touch the point, the rightmost point. So we have a 100 Newton meter load here, per meter load here, and then another 100 Newton per meter load here. Okay, so that it will be easier to draw our moment diagram by parts. Okay, so the induced moment by the 500 Newton load is actually 500 times what, times 8. So 500 times 8, this is actually located here. Okay, so we have 8. Sorry, 500 times 8 is actually 4,000. Okay, so 4,000 Newton meter. And of course, since it's a concentrated load, so the moment diagram will be a first degree curve. Okay, so there. So we have a triangular moment diagram for the concentrated beam, concentrated load. Since it's going upwards, so the moment should also be going upwards, and it is actually positive. Okay. Next one is the larger 100 Newton per meter load. This is the moment at A is actually, let's try to write it here. 100 times 8, that is the total length of the beam, and then times 8 over 2, or that's 4, which is the location of the centroid measured from point A. So this is actually 3,200. Okay. And then since the loading is horizontal, so the moment diagram will be second degree. Okay, second degree. So it's a parabolic spandrel. This is the vertex. This will be the vertex. And then let's project downwards here so that we can solve for the other for the last this moment. Okay. Okay. So the moment induced by the smaller 100 Newton per meter load about A is actually what, 100. Let's have a shortcut formula here. 100 times 4 squared over 2. Just like here, 100 times 8 squared over 2. That is for distributed loads only. So the value here is 800. So both are negative moments. Okay, let's indicate that one. Positive, negative, and negative. And then let's label the distances: 4 meters, 4 meters, 4 meters. Okay. Okay. So these are negative moments about A. All right. So actually, to draw our conjugate beam, we need to use the moment diagram by parts. So this moment diagram by parts is already our conjugate beam. All right. So to solve for before that, we actually need to show the the equivalent form of our supports at the conjugate beam. So since the endpoints of our real beam are simple supports, then those points at the conjugate beam are also actually simple supports. Okay, that's a property of the conjugate beam. If it's a fixed support, then it will be a free end at the conjugate beam. If it's a free end at the real beam, it will be a fixed support on the conjugate beam. Those are some of the properties. Okay, and then after that, actually, the drawing here, the diagrams here will actually be our loads at the conjugate beam. So this is actually our conjugate beam. And then since we have two diagrams here, this is actually only one. Okay, this is actually only one conjugate beam. This smaller parabolic spandrel here is actually attached to the given beam here. But since it will be harder for us to solve for some of the deflections, if we will attach this one to the conjugate beam, we'll just separate it here. So before solving for our maximum deflection, let us first determine the reaction at A on our conjugate beam. Okay, so let's have this as point. Sorry, this is actually our point A a while ago. So let's have this as point B. So let's solve for the reaction at point B. So taking sum of moments at point A at the conjugate beam that is equal to 0. Okay. So we have B times 8, which is the lever arm from A. And then since it's going upward, so we have positive. Let's have clockwise positive. And then since the positive moment due to the concentrated load is positive, so we also have an upward load here. So it will also cause a positive moment at the conjugate beam. So we have 1 half 4,000 times 8. This is the area of the load, okay, times its lever arm, which is actually 4. I mean, which is actually 8 over 3. That's one third of the length since it's a triangle. Okay. And then we have the two negative moments. So we have minus the area of the parabolic spandrel will be one third base times height. So we have one third, 3,200 for the larger one, times 8. And then the moment arm from A will be one fourth of 8. That is a geometric property of a parabolic spandrel. Okay. The next for the smaller spandrel, we have one third, 800 times 4, and then its distance will be or lever arm will be one fourth of 4. I'll just put some arrows here for us to understand there. Okay, so it will be equal to 0, and then which gives us the reaction that is negative. It's actually negative 9,200 over 3. So since it's a negative value, our direction is incorrect. So let's have a downward reaction at B. So therefore, we have a reaction at B that is 9,200 over 3 downwards. This is actually the value of C sub 1 at our double integration method. So at least we have we are much confident that this is our computation is correct. Okay, so now let's have to let's locate the maximum deflection of the given beam. Okay, so let us assume that the maximum deflection occurs here. So let us cut through this section at the moment diagram by parts, and then let's try to locate isolate it here. Let's Since we have the reaction at B at the conjugate beam, let us consider the left portion of the conjugate beam. So we have this load here, okay. Then we have this parabolic load here, and then we have the continuation, okay, and then a small parabolic load here. So we have 2-degree curve, 2-degree curve, and then this is actually x. Okay, let us assume that this distance is x. So if that distance is x, and this is 4 meters, so this is x minus 4. Okay, so since it's not the whole beam, then we must determine the magnitudes of the loads at these points. Okay, so using ratio and proportion for the red load here, that is actually y is to x, that is for the given load at the cutted section, that is equal to 4,000 divided by its length, that is 8. So this gives us y is equal to 500x. So this is 500x. Okay. Next, we have for the second degree curve, we will use the squared property of parabola. So let's have y is to x squared, since horizontal distances will be squared. That's the squared property of parabola. Y is to x squared is equal to what? The 3,200 load divided a moment divided by the square of 8. This gives us 500. Sorry, this is actually 50. Okay, 50x squared. Similarly, at the smaller spandrel, this is 50x minus 4 squared. Okay. Also, we have the reaction here. Sorry, 9,200 over 3. And then since we cut a section along the conjugate beam, there will be an internal shear and moment that will be exposed. But since we are trying to solve for the maximum deflection, okay, let's consider this portion already. Sorry. Okay, since we are trying to solve for the location of the maximum deflection, then we may have to equate the shear to 0, since point of 0 shear most of the time gives us the maximum moment. So shear is equal to 0. So taking summation of forces vertical is equal to 0 from the given portion of the conjugate beam, we have the equation. We have since upward is positive, so we have 1/2 500x by x, that is the area of the triangle here, and then minus 9,200 over 3, that is the downward reaction of the conjugate beam, and then minus the areas of the two parabolas since they are both downwards. So we have minus 1/3 50x squared by x. We just need to use the areas. Okay, no lever arms first, since we are trying to sum up forces. So minus 1/3 50x minus 4 squared times x minus 4. That is also equal to 0. So from there, we can solve for the value of x. Of course, it will also give us 4.1106 approximately, 0.63 meters. Okay, so this is the location of the maximum deflection measured from the leftmost support. Since this is greater than 4 meters, then our assumption is correct. So this is the correct value for x. And then for the maximum deflection, we take the moment at the conjugate beam here. We solve for the moment. Okay. So for the maximum moment, let's take the moments first. So this is let's have the triangular load 1/2 500x by x times its lever arm from the point here. So we have x over 3. Okay. Then minus 9,200 over 3 times its lever arm x minus one third of 50x squared by x times its lever arm. Since it's a parabolic spandrel again, so we have x over 4. And then lastly, we have one third 50x minus 4 squared by x minus 4 by x minus 4 over 4. This is the lever arm for the smaller spandrel. Okay, so the value of moment here is actually what negative 8007 approximately, since it's a decimal value. So negative 8007.386. So from there, we can solve for our maximum deflection. Since EI is constant all throughout the beam, so our moment diagram by parts is the same as the M over EI diagram. So let's take a note here. Since EI is constant, okay, I forgot to mention actually. So EI is constant, therefore the moment diagram is the same as the M over EI diagram. If the value of EI of the given beam is not constant all throughout, then we must have to draw the M over EI diagram first so that we could have our conjugate beam. But since EI is constant all throughout the beam, so this is actually our maximum moment of the conjugate beam. So we'll just have to divide it by EI to give us the maximum deflection. So therefore, our maximum deflection on the beam is also 8007.386 over EI. We just used a different method in solving for deflections. So this is our maximum deflection of the beam.
All right. Thank you, DJ, for sharing your expertise in solving strength of materials. And to our followers, thank you for watching us today. Hope DJ can join us again for our future episode. And to all our followers who send in their questions from Monday to Wednesday, that's Pacific Standard Time, Tuesday to Thursday in Manila, we will be solving them via Facebook Live again on Thursday, PST, and Friday in Manila. So see you next Thursday. God bless everyone and stay safe.